Okay, welcome to all of you, and a very good morning to all of you. And we have been talking about. I think yesterday we talked about the classical physics, the courses that you have already gone through in your graduation, and today we will try to move on because uh, classical physics uh, is not all about the universe. But the point is that up to the 19th century, the kind of laws that we talked about yesterday, the classical laws, the physicists of that time, they thought that the job is done. You have Maxwell's theory that's describing the uh, electromagnetic waves, and then you have Newtonian mechanics, where you have three laws of motion, and then you have universal law of gravitation. And people thought that this universe is a mechanical machine. And they were sure about it, that come on, we have done it, it's over. It's a mechanical machine, and we can predict everything about the universe. Because classical physics comes up with determinism. You can predict everything about any kind of classical phenomenon. As we understand that classical physics is applicable to macroscopic objects. It's applicable to the massive objects. So, what does it mean that classical physics is completely predictable? If I take an example of, say, a ball, right? If I know the initial conditions, I will throw this ball. If I know the initial conditions, I can exactly predict that where this ball will hit the ground, with what velocity the ball will hit the ground, at what point, at what position in the space the velocity of this ball will be. So I can exactly predict the future of this ball. And the same thing was presumed when we were in that zone of classical physics. It was presumed that we can understand everything about the universe. And universe is a classical machine. And this universe is running on the principles of classical physics. This was something that people had come up with the equations of classical physics. But to our surprise, universe is not a classical machine which can be predicted. Universe is actually giving us probabilities. When we know the initial conditions of the system and we try to detect that system tells me, come on, I'm made of probabilities. Now, say for example, if we take two individuals, individual A and individual B, both have brain. They are both human beings. The brain of both the humans is made of the same cells. It's made of the same atoms. But yet, the outcomes of the two brains are different. Because brain is quantum mechanical in nature. There are neurons. And even though the structure of both the brains is same, the outcomes of these brains are probabilistic. They are not accurate. They are not abstract. You cannot predict exactly. Getting my point? Now, the point is that the universe that we are seeing is not completely predictable. It's not going to give us the exact answers. So, Now you have to open another dogma. And what is that? And, and that's what we are going to talk about. And we are going to talk about the advent of what we call as old quantum mechanics. So certainly there are certain things that were basically giving us an indication that the classical physics is not working. We are using the laws of classical physics to explain certain phenomena, but we are not able to explain those phenomena. So that gave birth to what's called as old quantum mechanics. And you have already gone through this mechanics. So what is old quantum mechanics? It marks a transition from classical physics to the modern quantum theory, and spanning roughly from 1900 to 1925. So in this era, there is the advent of old quantum mechanics. So what are the main arguments? The first point is that, as I said, it was assumed that maybe this universe is a mechanical machine. You need better machines. If you have better machines, you can exactly predict what's going to happen in the universe. And this was the outcome of the classical laws of physics, right? But the universe was not actually responding in the same way as it was predicted in terms of the classical physics. So classical physics failed. It failed to explain some of the experimental observations that were taken during this era of 1900 to 1925. And what was that? It failed to explain the black body radiation law. And all of us know what a black body is. A black body, if you take an ideal black body, it's going to absorb all frequencies, all wavelengths, and it's going to emit all frequencies and all wavelengths. And then there is the famous photoelectric effect, atomic stability, the stability of atom, and the discrete spectra. These were the fundamental open questions in front of classical physics. And classical physics had a complete failure to explain these experimental outcomes. Black body radiation law, photoelectric effect, the stability of an atom, and then the discrete spectra of hydrogen atom. Now, if we talk about the black body radiation law, if we talk about the experimental observations, as we know what a black body is, when you perform an experiment and you just make a measurement, you make a measurement between the wavelength and the intensity of the radiation. And if we assume that light is, what is light in the classical world? Yes, wave. It's a wave. So if we assume that light is a wave, then if you move from higher wavelengths to the lower wavelengths, you should expect that the intensity of absorption or the intensity of the emission should go up exponentially. This is called as, what is this law called as? Can you tell me? This is a classical law that tells us that in a range of lower wavelengths, the intensity of the emission of the absorption should increase. Which law is this? This is Rayleigh-Jeans law. Yes. Okay, so Rayleigh-Jeans law predicted classic because the basic argument of Rayleigh-Jeans law is what? That light is an electromagnetic wave. It's a wave, and this wave is absorbed, this wave is emitted. And based on this assumption that light is a wave, Rayleigh and Jeans predicted what they predicted. They predicted that over the lower wavelengths, the intensity of emission or the absorption should increase. And you can see here you have different ranges of temperatures. At different temperatures, you take the measurements, okay, and you expect that the behavior should be exponential, right? But when you perform the experiment in the laboratory, the behavior is not, it's not exponential. The behavior is something like this, okay? You have the wavelength and then you have the intensity of absorption or emission, the curve between the two that we find in laboratory. The two curves are, the curve is, it's somehow resembling with a Gaussian curve. So the predictions of Rayleigh genes, what it says us that over small wavelengths, the intensity should increase. What does that mean? That means as you keep on decreasing the wavelength, the intensity of absorption or the emission should go on increasing. That means you are talking about infinity. You will have a catastrophe, what we call as ultraviolet catastrophe. But experimentally, when we perform the experiment in the laboratory, we don't see ultraviolet catastrophe. What we see a curve that goes up and comes down. Even at low wavelengths, the intensity of absorption is low. So there's a problem. The classical physics has a failure. It's not able to explain you the experimental observations of a black body radiation, which is absorbing or emitting those radiations. So the answer comes from Max Planck, because Max Planck takes a new window. It takes a window which does not fall in the framework of classical physics. Because in classical physics, the light is an electromagnetic wave. It's a completely wave kind of thing. So the Max Planck comes with an argument, no, I can explain this curve, the curve that goes up, that comes down. I can explain this curve if I assume that light is not a wave, but it's made up of the packets of energy. And the energy of each packet is given by h nu. H is the famous Planck's constant. Basically, it is this Planck's constant that differentiates you, that makes you a transition from classical physics to the quantum physics. So Planck's proposition was against the classical physics. Now people are in a different framework. They understand that what they had understood is not completely determining the nature of reality. It's not completely describing the universe. It's not completely describing the matter, the energy, the work, the power, the energy, whatever there is. It's not completely describing it. And then you have another important experimental observation. What is that? That is the famous photoelectric effect. Now, classical physics tells us what? It tells us that light is a wave. Now, if light is a wave, and you have an experiment in which you have a photosensitive metal, okay? You have a photosensitive metal, that means the metal is sensitive to the ultraviolet radiations, okay? So if I choose ultraviolet radiations, these ultraviolet radiations will pass through some collimator, through some window. When they hit the photosensitive metal, what happens? You have a current, what's called as photoelectric current, okay? So you presumably explain it that the falling of the light will eject the electrons. It will eject the electrons from photosensitive metal, and these electrons will be attracted by the anode, and you have the current, what's called as photoelectric current. Now, the point is to model it. These are the experimental observations. Now people are observing in their experiments and they are getting the results that are going against the classical laws of physics. Now the very first point which I can tell you is, if I assume that light is a wave, okay? Suppose this is a metal, okay? And the light falls on it. Now it will fall on it like a wave. And the wave has a nature of what? It has a nature of spreading, okay? So it spreads. So the light that's falling on my metal is what? What's my metal? Come on. You have a material in which you have free electrons. The electrons are free in the conduction band, okay? That's what's called as metal, right? So you have a metal, it has electrons, free electrons, and you have the light is hitting this metal. And the light is an electromagnetic wave, and if it is an electromagnetic wave, it has a nature of spreading. It's spreading like water waves. I have a stone, I'll drop it in the pond, you will have water waves. Are you getting my point? There's a transfer of energy. There's a spread of energy. Now, you have electrons. You have electrons in your metal, right? And the light is falling on the metal. And it is spreading on the metal. Now, if it is spreading on the metal, if I make small calculations, I will calculate, I will find it, the average energy that will be taken by an electron out of this spread of energy will be very small. It will be that much small that it's impossible for the electron to be removed from the metal. Are you getting my point? So, because if you rightly remember, you can tell me the observations of photoelectric effect. Come on. What are the observations? Yeah.
Electron is not ejected below a certain energy.
Yeah. Very good. Now, there we don't have any, we have frequency. Okay. You have some minimum frequency at which the electrons are ejected. Okay. Now, if the frequency is less than that minima that you're saying, and I increase the intensity of light, what's going to happen? Yeah, intensity, increasing intensity means, what does that mean? That means you are increasing, you're increasing the number. Okay. Yeah.
Number of electrons will increase, but energy will remain same.
The energy will remain same. Okay. Okay, come on. Any other argument? Where does there is confusion in the experimental observations? You are right that you see that if you increase the intensity of light and your frequency is less than that of the threshold frequency, there is no photoelectric current, which is against the classical laws of physics. Why? Because if I presumably assume, suppose there is some kind of object down there on the ground, okay, something like this. I will use one pebble, say half kg of pebble. I will leave it from this height. It may not hurt the table on the ground. But if instead of one pebble, I will use 1,00,000 pebbles, what do you expect from classical physics? 1,00,000 falling on this table, it will break. So by increasing the number, you are actually crashing the situation. Your problem should not be dependent on some fundamental energy, because I'm using the same energy, okay? And from this energy, with two, suppose I take one pebble, it falls, it does not break the table. I use 10 pebbles from the same height, it does not break the table. But if I will use, say, 10,000 pebbles from the same height means the same energy. the same potential energy, right? From the same height, you allow, say, 1 lakh pebbles to fall on the table, there's a complete chance that this table will break into the pieces, right? So this is classical physics. But what we are seeing here, we are increasing the intensity of the light many-fold, but there is no photoelectric current. The electron is not coming out. Now there's a problem. The classical physics fails to explain why there is no photoelectric current. And another argument that I gave is the spreading nature of electromagnetic wave. If I assume that light is a wave, then it must have a spreading nature. It should be impossible for an electron to leave the potential barrier of the metal, right? So that is what is called as photoelectric effect. So photoelectric effect could not be explained using the arguments of classical physics. And the explanation, as all of you know, the explanation comes from Einstein, because Einstein used the idea of Max Planck. He uses the idea, come on, light is not an electromagnetic wave, it's a quanta, it's made of packets of energy, okay? And this is your experimental observation that you see in the photoelectric effect. Up to certain frequency, there is no photoelectric current. Even if you are increasing the intensity of the light, that's a very important point, okay? So once you cross this threshold, now it is behaving exactly like Newtonian. You increase the intensity of light, the photoelectric current is increasing. So the answer to this photoelectric effect comes from Einstein's photoelectric equation, because he assumes that light is made of packets, and then you have that photoelectric equation. How it comes in action? Light is coming in terms of quantas, okay? Each quanta has an energy, h nu. Now a part of this energy is used to eject the electron from photosensitive metal, which is called as work function. And the rest of the energy is given to that electron in the form of kinetic energy. So your h nu is breaking into work function plus kinetic energy. So kinetic energy is E minus work function, right? So for work function, if we look at that equation, for work function we can use h nu naught. And h nu naught is representing what? The threshold frequency. Now that equation will explain the photoelectric effect. Because if nu, the frequency of the incoming radiation, is less than that of nu naught, you will have negative kinetic energy. And kinetic energy cannot be negative, so you will not have any photoelectric effect, even if you double, triple, quadruple the intensity of light. You will not have the photoelectric emission. Okay? But if nu is greater than nu naught, you will have a photoelectric effect. Now, see, here you have a quantum mechanical explanation to this problem. The classical physics is failing to explain the problem of photoelectric effect. Okay. Now you have another important argument falling, because the classical physics is failing here at the atomic scale. Talking about hydrogen atom, okay, it has a nucleus, it has an electron, and electron is a charge. And from classical electromagnetic theory, what we understand if a charge is accelerated, it will produce electromagnetic radiations, right? So an accelerated charge produces electromagnetic radiation. Now if we think about an electron, and this electron is revolving around the nucleus. Now electron has a charge, right? So electron has a charge. Now if electron has a charge and it's circling around the nucleus, at every point the direction of velocity is different. At every point the direction of velocity is different, because the direction of velocity at each point on the circle is given by a tangent drawn at that point, right? So there is changing velocity. Now if the velocity changes, what does that mean? That means the electron has acceleration. So if electron has acceleration, it should produce electromagnetic radiations. That means it should lose energy. It should lose energy continuously and it should fall into the nucleus. Okay? So from classical point of view, the atom should not exist like this. You cannot have an atom having a nucleus and electrons roaming around the nucleus, because these electrons should not exist outside the nucleus. But they exist. How do they exist? How do they exist? Come on. When we examine the spectra of these atoms, right? When we examine the spectra, we find discrete lines. Okay? So that gives us another argument that that classical physics has a complete failure in explaining the stability of an atom. And the answer to this question comes from Niels Bohr, the genius, who comes up with an argument. Now he has no explanation why things are happening like this, because your experiments are telling you that electrons are existing outside the nucleus. They have energies. They have discrete energies. Now to model this experiment, Heisenberg comes up with the postulate. What he says, come on, I don't know why it is happening, but electron is revolving only in those shells in which it does not radiate. So he starts his argument with this. He starts his postulate with this argument that electron is roaming around the nucleus, but wherever the electron is roaming, it does not lose energy. These are non-radiating shells. So he's coming up with a new argument. This argument is not classical argument, right? And there is another important argument. What's that? Yeah? The angular momentum of electron in the hydrogen atom is an integral multiple of h by 2 pi, where h is Planck's constant, right? So these are these are the postulates, these are the arguments which explain us that in atoms you have discrete energy levels. There are discrete energies. The electron can only have those discrete energies. There cannot be anything between these energies. In fact, the electron does not exist between these energies. It cannot be there. It's only there where it does not lose energy, where it does not, those regions are completely non-radiating. And this is your energy level diagram for hydrogen atom. You must have done it. You calculate the energy using Bohr's model, and you obtain this energy equal to minus 13.6 electron volt per m squared. Then you can see the quantization of energies. As you move away from the nucleus, the separation between the energy levels goes on decreasing. You can do this. You can make manipulation of these numbers to realize the quantization. So if you want to take out electron completely from hydrogen atom, you have to supply this much of energy so that the electron will completely lose the hydrogen atom. Now, you have classical framework. If we think about light, okay? Thinking about light, the classical physics has only one answer. What's that? The double slit experiment, the diffraction experiment, interference, polarization. All of these experiments are telling us that light is a wave, right? So this is one argument for light. It is a wave, and it is in contradiction to Planck's black body radiation law. It's in contradiction to photoelectric effect. It's in contradiction to Compton effect. There's a contradiction of this argument. So light has a dual nature, right? It has a dual nature. it is behaving like wave in certain circumstances, it's behaving like particle in some other circumstances. So, if light has a dual nature, then we have a man whose name is De Broglie. He comes up with an argument that if light can have a dual nature, the material particles can also have the dual nature. What we call as De Broglie equation, which is given by lambda equals h by p, where lambda is the wavelength and p is the momentum. It is basically the unification. It's a unification done by De Broglie, that he's unifying the wave nature with the particle nature. And if you look at this graph, if you can see those dots in this graph, these dots are representing the particle nature of the microscopic particle, and the rest is a wave. So you have a duality. If you talk about the position and the amplitude of a particle, and if you look at this graph, these dots are representing the particle positions, and the rest are the wave positions. Right? So this is your De Broglie equation that I talked about. Okay, it's unifying the wave nature with the particle nature. So, electron diffraction experiment is another confirmation of. It is a confirmation of this because De Broglie came up with an argument that material particles, which we assumed are particles, like electron is a particle, proton is a particle, neutron is a particle, atom is a particle, nucleus is a particle, a molecule is a group of particles. We can treat it as a particle. But De Broglie is saying us that it can act as a wave as well. And for that you have this Davison-Gerber experiment. Can anybody among you reveal this experiment to me? Yes? You have done it in your graduation. Come on. You remember that experiment where you have an electron gun, you have a collimator, then you have a crystal, and then you have a detector. Okay, you allow the electrons to hit the crystal. And crystal, what's so great about a crystal is it has a long-range order. It has periodicity, right? So if it has a periodicity, an electron is interacting with this crystal, and you are able to see the diffraction. Okay, if you remember that, you know that. Okay, you have a maximum hump at an angle equal to what degrees is that? 54 degrees. Okay, so this is already done. You understand it, that this is an experimental confirmation of De Broglie equation, telling us that material particles also have waves associated with them. Okay, then you know about Sommerfeld refining the elliptical order for the electrons and incorporating the relativistic corrections of that time. You know all that, you have done this all. And then you have correspondence principle trying to, because you are coming up with a new argument and your background is filled with classical physics. Okay, so Bohr is coming up with the principle known as correspondence principle, and it tells you that if the quantum numbers are extremely large, then your quantum system is coming back to the classical system. This is your correspondence principle. And you have certain explanations like electron is jumping between the states, right? Now, can it exist between the states? No, it cannot exist. Now, is this a mechanical jump? Somebody jumping from this window? Yeah? So what is it? It's something that you cannot physically describe. It's like teleportation. It's like disappearing somewhere and appearing somewhere. Okay? So you have the discrete states. Between these states, there is a transition of these electrons. Then Compton effect. Come on, I want you to tell me something about the Compton effect. Yes? Yeah, come on, describe it to me. Yeah. Speak sound, I should listen it. Yeah. Come on. You have a photon. This photon is hitting a particle like electron, and the photon has energy. Then this photon has a recoil energy. Then that particle has a recoil energy. Then you make a calculation and you calculate the shift. You calculate the shift in wavelength. And can you tell me what's that equal to? Lambda minus lambda naught is h by m naught c times 1 minus cos phi. Phi is the angle between the incidence and the scattering. And Compton effect is basically a further confirmation of particle nature of light. Because if you rightly remember what I said if light is a wave, it has a spreading nature. Now think about Compton's effect, where a wave is coming and hitting a particle. So what's going to happen? There should be redistribution of the energy, because wave has a nature of spreading, but that's not the case. You are treating your problem like particles, right? So photon is taken as a particle to explain Compton effect, confirming light's particle nature, in addition to the photoelectric effect and Planck's blackbody radiation law. So what are the achievements? It explains, now you see, you must have seen that there are some crazy stuffs involved in explaining these quantum mechanical effects, like Bohr model of hydrogen atom, where you treat some of the regions which are non-radiating, and there's no explanation for that, right? You're missing that explanation. But you will see when you will go to quantum mechanical formalism, and when you will solve the problem of hydrogen atom, you will see that you will naturally obtain, mathematically, you will naturally obtain these quantization rules. You will naturally obtain the energy quantization. You will naturally obtain the quantization of angular momentum. So it explains blackbody radiation law, photoelectric effect, hydrogen spectrum, and atomic stability. And it has a failure. It fails to explain the spin of the electron, the fine structure. If you rightly look into the Balmer series of hydrogen atom, you will see each energy level is split into many energy levels. It doesn't have any explanation for that. And I will put this as is, because it is also falling in the framework of all the quantum mechanics, and it becomes the bone of the modern quantum mechanics, the uncertainty principle. And then you have a formalism, Schrödinger's and Heisenberg, and this formalism, roughly between 25 to 26, what they did, they developed wave and matrix mechanics, forming the modern quantum theory, right? So this is what we are going to do in the course. This is something that we're going to learn. This is something we're going to understand, and this is something that we have to be skilled of. So modern quantum mechanics, it unified previous ideas into a complete framework, okay? So you have the ideas that are coming from the old quantum mechanics. Now you have to model them, okay? You model them in the framework of quantum mechanics and explaining your atomic and subatomic behavior. Now see, when we talked about the classical physics, we chose everything as a macroscopic object. But if in reality we look into it, we are basically made of the microscopic particles. So what appears to be more fundamental than that of the classical physics? The quantum physics seems to be more fundamental, even though the quantum physics also has its drawbacks. It has its limitations. It cannot explain you each and everything regarding the nature. In fact, the answers will come in terms of probabilities. You will not have discrete deterministic answers coming from quantum mechanics, but it is certainly more fundamental than that of the classical physics. So these are the applications. Now to conclude this, all quantum mechanics bridged the classical and the modern one, okay? A revolution in understanding. So now if anybody wants to have any kind of discussion on the titles we have talked about, you can infer, you can talk about them. Come on. You're exhausted?
No, so much.
Then why you don't have any interaction? So, so now we will be taking on in our next interaction. We'll take on. We'll start with our formalism. We'll start with the quantum mechanics, where we will start with the arguments of the postulates of modern quantum mechanics. So, can you please